I pointed out that there is another way of measuring performance of classifiers, which is through this idea of RSC. And the one thing that I wanted to emphasize, because it's often confusing to people. So this RSC is really a property of the family of classifier indexed by threshold. So it's not a measure of the performance of a single classifier. If you give me a single classifier, it's just a binary decision. So give me X, I give you the binary decision. We can't do the RSC. Is in fact it's just going to be one point here. So there's one false positive rate for it. There's one true positive rate, and then so false positive rate is the probability that I declare y hat predict y equal 1. So y hat is 1 given that the true label y is 0, and the true positive rate is the probability that I predict true label to be predicted label to be 1. So y hat is 1 given that y is equal to 1. So the easiest way is to see this. The definition of true positive rate and false positive rate is through this idea of conditioning. So I have like 4 quantities basically. Probability y hat equal 1 given y equal 1. Probability of y hat equal 1 given that y is equal to 0, and 2 other quantity y hat is equal to 0 given that y is equal to 1. The probability of y hat is equal to 0 given that y equal to 0. And so so this is called true positive rate. This is false positive rate. This you can imagine is called false negative rate. Yes, this is true negative rate. Yeah. So negative is like 0, positive is 1, and so you have true positive rate. Rate means like probability or fraction. So true positive rate. The true label is positive and your prediction is positive. False positive rate, you have true label is not positive, negative, but you declare positive, so it's a false positive. And if it's a false negative, because you're predicting negative, but the true label is not negative, and it's a true label. So these two, you can imagine, these are like related to like this, because binary classification, when you predict 1, so you're not predicting 0 otherwise. So mutually exclusive events. And so 1 is 1 minus the other, so you just can focus on these two. And so it's basically the probability of declaring positive under the two classes. And so for a single classifier, you get just one of these and one of these, and then a weighted average of them will give you the classification error, the risk that we talked about. It's easy to calculate that. So basically, the risk of being given these, what would be the risk? Let's say if you want to like the risk, let's say the classification will give you these numbers.
False negative.
False positive rate plus
Negative.
right, but that wouldn't work because like potentially this would be 2, because the probabilities are like would be close to 1. So there's like a slight tweak. So these are conditional probability. Right. So what I want, like if you want to calculate the probability of error, the probability of our risk was this probability of y hat not equal to y for the 0, 1 block. Right. You can go ahead by condition. The condition on y being 0, condition on y being 1, but then you have to also multiply by the probability. Right. So you get anyone help me? For example, I get false positive rate. So is the probability of making an error under 0 times,
The marginal.
yeah, the marginal probability of y equals 0 plus false negative rate times the probability of y equal 1. So if we call this pi 1, I think if you look at Wikipedia, sometimes it's called prevalence. Prevalence is the volume that makes this, I believe. Case. So this would be 1 minus pi 1. And so this would be false positive rate times, or you can say pi 0 if you want. Be a little bit easier. Plus 1 minus true positive rate times pi 1, something like that. So you have this information, then you can calculate the misclassification error. But you can see the misclassification error depends on the marginal probability it passes, prevalence if you want, base rate, some people call it base rate. And the thing is that if one of them is very close to 0, then that quantity doesn't have an effect. So for example, let's say the number of positives is very small, then this term, because of pi 1 being very small, is going to be close to 0. So it doesn't matter if you do, if your false negative rate is high, or if your true positive rate is small. So it doesn't tell you much about the performance. And then in fact, the majority classifier, for example, classifier that classifies everything as 0, that can't have any false positive, right? So the one that just declares 0 always, maybe it's not even the majority, but it would be majority because if pi 0 is equal to 1, the majority of training would have would be negative, and so we declare negative. So the majority rule would have this would be 0, and this is very close to 0, so you take like point maybe 97% accuracy. And that one might be misleading because if you care about the true positive rates, the true positive rate might be very horrible. And in fact, in that case, if it's 0, so if you declare 0, then true positive rate is 0 as well, because you never declare positive. So, so for that reason, the ROC, the view of so discounting for base probabilities and just viewing as these class like conditional probabilities, basically detection or the classification. These are maybe more interesting or more robust. Right? So in measuring the performance of classifiers. And if you haven't found the classifiers, then you would have this tau, let's say a threshold, but it could be a parameter, but usually people thought that RCs were classifiers that look like this. So the threshold is a particular function. So this you can think of as the probability, your estimate of the probability that's y equal to 1 given x. So this is just our estimate of the regression function. Remember, this is just usually a prediction of this probability that y equal 1 given x is equal to x. That's our prediction we had. So this is something we think you have on the threshold, and if it's above a certain number, we say class 1. If it's below a certain number, we say class 0. So let's predict class 0. And that threshold, if our losses misclassification is 1/2, if your loss changes, now we've seen the whole problem. We have a threshold here, so any kind of threshold here is sort of valid depending on the loss function. And so as I vary this threshold, I'm going to trace different points. For each one of these classifiers, I have a false positive rate and a true positive rate of different pair. That pair is called the ROC. And then a measure of how good it is the area under it. And so like a random decision would be, or would have this ROC of this 45-degree line. And the perfect classifier would be the one that jumps from 0 to 1 and goes all the way. And so in practice, you get something in between. And the closer you are to the ideal classifier, the better. And RA is like the area under the curve, we call it ABC. But ABC of ROC curve is a good measure. Area under the curve of the ROC curve. If it's the perfect classifier, you get 1. Because the area would be just the whole thing. If you have the random classifier, you get 1/2. That's the area of this triangle. In practice, your classifier would lie somewhere in between, so you get the area between like 0.5 and 1. The closer to 1, the better. And it has an interpretation. I have like a proof in the notes if you want, that this AUC is basically can be interpreted as a probability. If I randomly pick one positive case and one negative case, what is the chance that it's like the probability that I score a positive case. So let's say X is from I don't know if we have a notation for this. Let's say P1 and X prime is from P0. So this is the class conditional under. So remember this notation. Okay, so let me go down here better. So I don't know if I introduced this notation, but if you go back, one way to model the joint distribution of X and Y is to specify the probability of, or the density, right? The density of X given Y equal to 0, and the density of X given 1. So these are the class conditional densities, or more generally, there's going to be what we call the probability measure distribution. I might write it, I don't know, in the notes as nu, d nu of X, d nu 1 of X. These are just the probability distribution. So if I sample the result, like, for example, this is the Gaussian distribution. So if I sample 1x from the positive distribution and 1x from the negative distribution, independent of each other, then the probability that eta hat of X is bigger than eta hat of X prime would be that AUC under ROC. And this probability is over just the X and X prime. Randomly pick a test point from the positive distribution and the test point from the negative distribution, the chance that the score, so you can think of the eta hat of X as your score, somewhere between 0 and 1. The closer to 1, the closer the prediction to 1. So the probability to use for the positive example higher than the negative example would be exactly this area under the curve of ROC. So it has this nice interpretation. Okay, it's not a very difficult result, but as was pointed out last time, it doesn't tell you the entire story. It's just a number. So there could be 2 different ROCs that have the same AUC, but behave differently, so they might cross each other. And so in that case, it depends what double false positive rate you want. Yes.
So if, like you said, that they generate the graph by varying tau from 0 to 1, right?
Yes, yes.
But are we guaranteed that if tau varies from 0 to 1, false positive rate will also vary from 0 to 1?
So tau we don't vary from 0 to 1. Tau you vary from the entire range, like negative infinity to infinity. That's the entire range. In this case, yes. I mean, this case, yes. If your classifier, let's say eta hat is between 0 and 1, right? So we vary the threshold from 0, like negative infinity to infinity. In general, this may not be the it may not be exactly probability. It might be like something related to probability, like the logic. We'll see maybe. But let's say if this probability is 0 to 1. So let's say if tau is less than 0, right? The chance that this is bigger than 0 is 1. So it's always going to be 1. Right? And if it's bigger than 1, this is always going to be 0. Right, so basically at some point you get the classifier that classifies perfectly as 0 and perfectly at 1. Okay, and those are these 2 points. So the classifier that always outputs 1 at true positive rate, which is 1, and false positive rate, which is 1. And the one that outputs 0 is going to be here. So if you vary the threshold such that it just falls below the range or above the range of eta hat, then this would happen. And if eta hat is really probability, then it's 0 ones. Sometimes you have something which is in bijection, like 1-to-1 correspondence rate. The probably, so for example, in a lot of neural network architectures, you output the logic. So the log of this divided by 1 minus the log. So that would be a real number. So we'll see that. So then you vary from negative. Okay, any other question? Yeah.
Why can you have two ROCs?
Sorry?
Why don't you have the second?
Yeah, so this is usually to use this to compare to estimators or to classifiers. So what we have here is I have one, for example, for this is my, let's say, eta hat 1, and then I have another one for eta hat 2. Could be like that. Okay. So we can try to compare them using this, but this picture tells you a good story. So if you care about like small false positive rates, this is gonna do better. Unfortunately, this blue one is not very appealing, so maybe goes like that. If you allow for higher false positive rates, then the blue one is better. So it depends on your tolerance for false positive rate. And so depending on your application, so you could okay, so you can just output this and let people decide. Yes.
Like in practice, the way you'd make one of these is you let tau take its range and then
Yes.
plot points for a given classifier, like eta 1 in the example you just drew. The way you make that blue line is
Yeah.
you let tau take its range and then plot the FPR and TPR along.
Yes, exactly. So in practice, actually, what you do is you estimate these probabilities, right? So the true false positive rate is at the level population, which you don't have. So this, remember, this is like
In our test data.
it is for a test data, yeah. So it's like your let's say f hat or f tau of x, given that y is not equal to 0. So this is 1, yeah, so do it properly. This would be the probability of f tau of x equal 1, given that y is equal to 0. So it depends on the joint distribution xy for an unknown test, which is dependent on that unknown probability distribution. But in practice, again, you can approximate this by an average, right? So you know how to do it by just a frequency. So you can take like a test set, right? And you have xi's and yi's, and then this would be the fraction of point that you classify 1 within the 0. You can write it as those indicators you want. Summation I from 1 to m, let's say, indicator f of tau of xi not, or say 1, and yi is equal to 0 divided by summation yi equal to 0. So that's how you calculate it, and this is for a single tau. And this you do the same for the particular tau for this one, and then that will give you a point here, and then you vary. If you think about it, because of the discrete nature of this, you don't need to compute all the taus. And because in the end, you're going to have only this many values of eta hat. And so eta hat takes, like you have like m test points and eta hat takes this many values. And so for tau in between those values, things wouldn't change, right? So you just can just sort all these values and just your value threshold along those values. And in between, it's just a big flat. So in practice, you like have a stepwise approximation. Right. But all that we need to know about ROCs. Any other? So, yeah.
Yes, so when you have a different tau, you would have like different like ROC.
No, so the entire range of tau would produce a single ROC. So for a given tau, you get just one point here. So you get like this point. And then you vary tau, you get another point. Right, so for each tau, you get a classifier. Basically, once you fix tau, this is a classifier that has a false positive rate and true positive rate. So that would indicate one point of this there. As you vary, you trace out the entire. Sounds good. It might be a little bit tricky because you'd see that people just say, okay, this is my classifier, this is ROC, but you have to remember they're varying some threshold. So it's like most of these classifiers that we build have this built-in threshold. Because usually they're putting the probabilities or the logics. And so there's this tuning that they all share, and that's what they do. Okay. So there are other variations. So given these four probabilities, you can see other measures. So if you look up like in Wikipedia, no, and like if I'm not wrong, I usually mix these up, but this is also called sensitivity. And 1 minus this is called the specificity. So 1 minus the specificity, I believe. And so if you check sensitivity and specificity, you see that there's a long list of other measures. And these also have other names. So this is also called recall. Different terminologies for different literature, different subset of people. True positive rate sensitivity recall. There's another concept which is called precision. And then there's a precision recall care. So you plot this against not a specificity or a PR, but against precision. So what is precision? Precision is basically this probability flipped. So instead of calculating the probability of y hat equal 1 given y equal 1, you calculate the probability of y equal 1 given y hat equal 1. Okay, so what I would calculate is, so precision, also called predictive positive value, according to Wikipedia. So precision. So what it is the probability of y equal 1, the true label equal 1, given that y hat is equal to 1. Okay, so that's precision, or PPV. And then probability of y equal 1, like I said, y hat equal 1 given y equal 1 is just the true positive rate, or recall, or many other names. So then you often one of the things that people plot is precision versus recall. So they plot, they call PR curve, precision versus recall. So you plot it and it just goes down something like that. And so the advantage is this somehow kind of captures that class imbalance issue. So if you, for example, so first we can calculate these. So this you know, and this you can calculate based on those four probabilities on the base probability. So this is by Bayes' rule, you can translate it back. So it's gonna be the probability of y hat equal 1 given 1, so this times something divided by something. Okay, so this can be, so this precision can be calculated based on the RC and the base probability. So you don't need any extra information, but it's helpful because this quantity is of interest. So sometimes you want to know how, like what fraction of the ones that you declared positive are actually true labels. And these two together form a trade-off. So the fraction of the true ones that you declare y. So for example, if I always declare 1, my recall would be 1, but this will not be 1. Okay, so this sort of has this false positive baked in. And it's really good in cases where true positives are really scarce and you really want to know what fraction of the ones that you produce are actually true. Sounds good. But this has like the class probabilities baked into it. So it's not like the RSC is this entire of the class probability. So it's a nice mix of the idea of RSC and it doesn't suffer as much from the class imbalance than just aggregate misclassification. And then there's an area under this for which I don't know. So it's called AUC under the PR curve and so on. Good. So these I think are enough. And then this is also like 1 minus FDR, false discovery rate, which is the probability that y is 0 given y hat equal 1. So you discover something, but it's false. And this false discovery rate is very popular in statistics for in the hypothesis and quantum hypothesis. So the terminology of hypothesis testing and classifications will overlap because there is a nice connection. We haven't talked about that, but maybe some. That's just good to know. So the main thing is the ROC, and then if you flip the true positive rate around, you get the precision, and then you plot the precision against the PPR, you get this precision rate called that. Sounds good? Okay. Questions? So you're done with this chapter for now. I want to go back to this idea, and if you recall, one of the issues that we like arises in the local averaging, especially in this partitioning that we did, is this step of dimensionality that we saw, which is suggesting that as dimension grows, so the number of features, especially like a continuous case grows, then the variance suffers greatly, and the world performance suffers as a result. And so one question is that can we mitigate this? And one approach is to assume that the true function comes from a certain like smaller class of functions. So this doesn't assume any sort of regularity. Let's say in this point, at this point we assume Lipschitz regularity, but Lipschitz is very general. But if I enforce more structure, let's say if I assume that my functions are from parametric class, and that parametric class is simple, especially for example linear functions that you might have seen before, then I can get around this. So instead of having a rate, which so the optimal rate in this case, in the case of Lipschitz would equal 2 over 2 plus d, and it gets like very slow as d grows, I might pay like a much more benign price in dimension. If I, for example, I know that my actual function is linear. So for that reason, people often start doing or like approaching this problem as imposing a model for the class of functions that we have, and then trying to find within that class an estimator that sort of fits the training data. So I want to back off a little bit to give you the general picture. Remember that, so this is like a chapter that we talk about for a while, and we're going to call it empirical risk minimization. So before talking about the function class, let's go back and so I want to give you a general approach to constructing estimators, which is then amenable to reducing the function class to a specific class. So the idea is that if you recall, the original way that we looked at classification was to minimize the risk. So we tried to find a function f that minimizes this risk for a particular loss function. And in practice, we approximated this loss using, let's say, test sample. Or I can approximate using training sample for a single fixed x. So suppose I have training data. So I have x1 up to x, y1 up to x and yn. And so what I can do is I can approximate this risk by the empirical version. So we're going to call this r hat, what I called. But this is also called like r of training, if you remember. I think I called it like this. I from 1 to n, L of yi, f of xi. Okay, so I can evaluate this expectation as an average. Approximate this expectation by an average over the training group, which replace y and x paired with yi with I. I get this empirical average, or this is my empirical risk, which is also just the training risk or training error in our previous terminology, theory risk, aka training error or risk. And because now I have an estimate, and for a fixed f, this is a good estimate, it's unbiased and converges by the law of Eichler, that this one is by fixed f. So I have a good estimate. Now I want to minimize this, which would lead to that optimal rule, which was based on the conditional minimizing the conditional posterior loss or the posterior loss, the conditional probability of y equal 1 given x in the case of the one loss. Instead of doing that, I can just directly minimize this. Yeah, I can say instead of trying to minimize the population loss, which I don't know, I have this, I'm going to minimize this. I'm going to argument over r hat of f over f, or argument basically 1 over n summation I from 1 to n, L of yi, f of xi. Okay, so imagine L is just the 0-1 loss. Then if I do this, you can easily show, if this replace it with 0-1 loss, you can easily show that minimizing this would give you that plug-in optimal rule. So try to minimize this. Basically, this is like a p hat applied to the generic sample. I don't argue, but if you argue for yourself, this is exactly the same type of argument that we did that led to the optimal rule. This will lead you to plug-in optimal. So the solution of this would be plug-in optimal rule in the case where x is discrete. So when x is not discrete, this is not a bad estimate. In the case where x is continuous, the slope would be like a plug-in rule, but then the plug-in rule would be like trivial, would be that interpolating rule, so it wouldn't be useful. So in general, when I try to do it with the 0, 1 loss, I can make this 0, I can find the function that interpolates perfectly. And that wouldn't be very useful. So for that reason, you'd introduce some restriction here. So you'd assume that instead of minimizing this over the all possible functions, I'm going to restrict it to the class of functions. Okay, and this is the general blueprint for all these empirical risk minimizations. So depending on the class, I get different estimators, but by controlling the class, I can avoid that interpolation issue. So this class F is the class of functions from the sample space to, let's say 0, 1, in the binary case, over which, so we minimize basically. Minimize. The empirical risk. So this idea is very general. I can do it, for example, in the context of regression with the, so this is for classification. But I can do it for regression. So very general idea can be done in principle, at least for any loss function. For example, if the problem is regression, then I can take L to be the quadratic loss, y minus y hat. Then our empirical risk minimizer would be argmin f in some class, function class, 1 over n summation I from 1 to n. I'm going to replace this L of y and f xi with just this loss, you get yi. Which might look very familiar. Okay. So if you see non-parametric regression, that's how you do it, right? Like at least a loss will look like that, and then I'm minimizing it over class of functions. Again, for regression, things are easier to analyze, so or like look at. So we're going to first look at regression and then go back to classification. The regression has a nice feature that this loss function is smooth. Right, so when I form this ERM, so let's call this the ERM, empirical risk minimum ERM estimator. If you want, I can usually solve this using, for example, if this is a parametric family, there's a parameter and a parametric form is smooth, then I can try to solve this by using numerical techniques, as we'll see. The 0, 1 loss is problematic because it's discontinuous. Oftentimes you replace it with a surrogate loss function, and then you minimize that instead of the 0. So it's the idea of empirical risk minimization. Sort of clear. So this encompasses a large class of estimators, and many good estimators, classical estimators fall within this category.
So what does the class capital F eliminate that deals with that interpolation problem?
So at this point, I'm leaving it very general, but there are many choices, and we're going to see the most simple one. What is the most simple class? So yeah, so this is the regression problem, but linear regression, the class of linear functions. Okay. So the class of linear functions, that would deal with that. Like here's the dimensionality, issuing the variance. But assuming that the true function is also linear, then you would pay a bias price. One of the issues is that by restricting this class to be small, I can control the variance. But if the actual function is outside this class, then I pay a big price in the bias. Yes. So what we're going to do, so for example, the simplest case is f being the class of, usually the class of affine function, but I'm going to write it as f theta like this, where f theta of x is just theta transpose x. Here, let's say our sample space is Rd. So these are really functions from Rd to 1. Okay, so this notation, in this notation, this is theta is a parameter in Rd, and x is also a vector in Rd. So really f theta of x is like theta 1 up to theta d transpose times x1 up to xd. If you recall your vector matrix, this is like theta 1 to theta d, and then x1 up to xd. So you do the matrix multiplication. This is really theta 1, theta I, xi, I from 1 to d. This is really another way of writing this is just inner product. These are all different notations. So it's the usual inner product between theta and x, which I write in theta transpose x like this. So if you write it like this, you can immediately see it's linear. It's basically a linear combination of the components. The vector, each of these parameters theta. So that's a general form for a linear function. Oftentimes you'd add an intercept as well. So you would look at f theta and b, let's say, that look like theta transpose x plus b, where b is a scalar. B is in R. In practice, we'll do that, but for now, I'm just gonna drop this. If you have, say, like inversion, there are easy ways of absorbing this into that by introducing an extra feature of 1. So you can write it as theta and b, and then x and 1. So this is, sorry, theta transpose. So this would be like theta b transpose x1. And so if I add just one element, like a fixed element of 1 to my feature vector, so there's an RD in RD, both are in RD. This can be thought of as a new parameter, and this is a new feature. So this way you can just treat these are called affine functions as like reduce it to the linear case, don't carry the intercept. This is called the intercept of bias in ML terminology. Reasons that are unclear to me, but it's not unclear, but it's very confusing to call this bias because usually bias for statisticians is something that we talked about. But a statistician called this an intercept, and also call it bias. These are called weights, these are biases, weights and biases. For statisticians, they're all parameters. And so I'm going to work with this for now. So let's restrict to this. So this is the class of linear functions. Class of linear functions on RD. Okay, so that's perhaps the simplest class. There's a class which is simpler than this, which is the class of constant functions. Okay, you can go there if you want. Just assume that the f is constant. And if you minimize this already class of constant function, what would you get? The mean, the empirical mean. So you classify the Phoenix by the empirical mean. So that's similar to the majority rule classifier in the classification. That's the baseline. So if I ignore all the features, that's equivalent to taking this class, we pass all constant functions. And so in that case, I would have an estimator of the regression function which is constant, and it's just y bar. And you can use it as a baseline. If you can't beat that, then there's no point in continuing. But then the next level is like these linear. Okay, so any questions about this? So let's plug this into that problem. So now so with the linear class, let's call this F-lin. So with the linear class, F-lin, my estimator would be F hat is argument so I'm going to plug in, because they're all looking like this, I'm going to plug this 4 into that and then optimize over theta. Okay, so that's what we need. It's a parametric class. It's parametric like this parameter theta. Once I know theta, I know the function. So there's a correspondence basically between d-dimensional parameters and this function class. So let's say f is any function, and f-lin is in one-to-one correspondence with a vector, any function f theta is in one-to-one correspondence with a vector theta in Rd. So our f hat would be just f of theta hat, or let's say this function would be like that, where theta hat is minimizing 1 over n summation I from 1 to n yi minus f theta of x. Okay, instead of minimizing over the class of functions is equivalent to minimizing over state. I can replace so f in f by f theta and then by theta. And if you plug in the form, this is equal to, let's say, equal argument theta in this case is Rd. But I can also restrict my theta if you want, or if I want. So Rd 1 over n summation I from 1 to n yi. I also usually write this, sorry, xi. At this point, I usually write the training data with lowercase symbols. It's a little bit hard to see in writing, but for most of the future developments, things are small. These are realizations of training data. Rather than writing it as random variables, it's a little bit easier to do this, or more natural. So it's going to be yi minus f theta of xi squared. Oh, this is the same thing. I just want to replace this with yi minus theta transpose xi squared. Okay, so I just replace the theta with that. And so this is an optimization problem in Rd, which we can hopefully solve, and you hopefully know how to solve. So this is really linear regression. This problem is unusual linear. Yes.
You said that by restricting our f to a certain domain, we'll get rid of the plus of dimensionality, right?
Yes.
But here we still are dealing with theta belongs to R.
Yes, theta belongs to Rd, but you're dealing with Kirchhoff dimensionality. The Kirchhoff dimensionality is not that the parameter is Rd, because the data is also in Rd, right? The Kirchhoff dimensionality is this horrible rate. So the fact that the variance goes like h to the d, and then which results in this rate, which is like 1 over d. I haven't shown you the rate for yeah. So there is dimension, so we have to have like d dimensions, but since you asked, we can now do an analysis. So we can try to analyze this. You'll see how D appears. Let's do that. Let's do the analysis. So what I'm gonna do actually for the most of this chapter is try to solve this using a general technique. The so-called gradient descent, which will work for any differentiable loss function under very general settings. But this particular problem, it's a quadratic problem, it's convex, it has a it's actually the loss is strictly convex, and so it has a unique global minimum, like solution global minimum, which can be obtained by differentiation. And then you can actually solve this subjective for the actual, there's a closed form solution. So we're gonna do that. Hopefully most of you know that already. But then we switch to how to solve this using a more general numerical technique, which can be extended to other parameters. Yes.
Just before we move on,
Yeah.
so back at the sort of head of this section, I don't know, like, if you minimize the empirical risk for the training error, you
Yeah.
get the plug-in,
Yes.
you get that, you said we're not gonna do this argument because we've done it a few times, but can you remind me, like, when you're going to argue that minimizing this gives the plug-in optimal rule, what's the next thing you do per se?
So you want that argument, you're talking about the argument to go from.
Minimizing this gives the plug-in optimal rule.
Right, okay, so the idea is, if you think about this, the different ways of doing it. So we can do it for the 0-1 loss, maybe we do it with 0-1 loss. So that's actually a homework problem in the book, but let's try. So this would be the risk. This would be 1/n summation I from 1 to n. Indicator y not equal to f of x. Right? So do you remember how we went about arguing that the minimizer for this was that optimal rule formula? Anyone remembers how we did that? So we said let's condition, right, on y not equal to x, given x is equal to x times the probability that x is equal to x, right? These probabilities do not are not in our hand, so we can't minimize that. But once I fix this, this is just going to be f of little x, which I can decide. So I'm going to decide this f of x for every x to minimize this conditional probability. Okay, so that was the argument. So what would happen here is you can actually write this as, let's say, p hat of, if you want y, let's call this y hat. Y hat is bad. I don't know what should I call them. Let's say y bar not equal to f of x bar, where x bar and y bar is a generic point distributed like p hat. So this is a little bit abstract, but this p hat is the distribution that puts uniform mass on the training data. So if I want to write it in the language of measure theory, it's like 1/n sum I from 1 to n, delta xi yi. Delta xi yi is a point mass, right? Xi yi, so it's like a probability measure that, so let's say in 2 dimensions, this is xi, this is x and y, say the x direction and y direction. I have these training data. So let's say x1, y1, there's this 1 point. And then x2, y2 could be here. And then another one could be here. So these are x1. So a probability distribution that puts mass 1/n on each one of them is a discrete probability distribution. And I can sample from this distribution by just drawing like one of them at random. Okay, drawing from this distribution is just taking one of these points as random. So that's a valid probability distribution. It's a discrete distribution, takes n values, each of them is one of these. So that's the p hat. And if I draw a pair from this p hat, it's equivalent to just drawing one of these points. And then you can see that this would be just the probability. So the thing that I wrote, the 1 over n summation, that's the probability under this distribution. Right? And so because this is a valid probability, all of that goes true. And everywhere we get this p hat instead of p. And that p hat is just these averages. Right? Yes.
And there, you mentioned the test error, but you did all the stuff with the
This
train
training.
error.
Right.
So what was that?
No, this is training. So what I'm trying to do is now approximate the risk using my training data and use it to train. Because I'm trying to train, I'm still going to call this training error. If we at the end want to, because at this point I don't have any classifier, I don't have to worry about dependence. But once I do this, then my f hat at this point at the end would depend on the training data. Now, if I want to validate it, I need it like a separate stuff. So this is the idea of using the empirical averages to actually construct the estimate. So we're at the point that we want to use this, our estimate of the risk to actually construct the estimate. So that would be the training risk, or like whatever you want to call it, empirical risk, and we use it to minimize and find F. Any other questions? So by the way, this thing that I mentioned, this p hat, the thing that this is called the empirical distribution. It's a very important object in the statistics. So it captures the information about the data except the ordering of the data. Okay, so if I give you this picture, if I remove the labels, you know what the training data was, but you don't know in which order it came in. Or if it's discrete, I might lose some of the distinctions. So some of the points might lie on top of each other. So I get, for example, 2 of the points lie here, I get 2 over n. In the discrete case, you lose more, but that captures all the information in the data. So it's sort of, in a sense, sufficient. It's a sufficient statistic. Okay, so going back to this, how do we solve this? Have you seen solution? Regular solution. Sorry?
First order condition.
First order condition, which is just take the derivatives equal to 0 and solve. The first order condition, if there is an optimal solution, the derivative of the gradient in this case, it's a multivariate, the gradient has to be 0. Okay. If the gradient is 0, that's called the first order condition, you get a stationary point, but because in this case things are convex, and you know there is a global minimum, you know it's unique, there should be one stationary point, and that should be the minimum. Okay. So the idea is like take the if we call this what should we call this? I don't know, maybe L theta. Take the gradient L theta, say it equal to 0. And the solution, there's a unique solution if you want first order conditions, or their optimality conditions, for the above optimization problem. So that would give you like theta hat. So let's maybe write it in a more compact form if you have seen it. If I introduce this notation, the design matrix for it, this is collecting the data points as its rows. So x1 transpose is the first row, x2 transpose second row, up to the xn transpose. This is going to be an n by d matrix. And then I'm going to collect the y's into a vector as well. And so this is in Rn. Then I can write the loss. This loss function is really nothing but 1 over n. Anyone knows what the loss function would look like in this notation if I have a design matrix n by b? And y is like that. So it will be x times theta. Each row of x gets multiplied by theta. So you can think of this as, because this is scalar, it's equal to its transpose, which is also xi transpose theta. So these are the same thing. And you can see that this is going to be x1 transpose theta up to xn transpose theta. So the rows of x theta would be the values of this regression function at those training data. And then I'm going to compare it with y. So basically, it's just going to be summation I from 1 to n. This vector y minus x theta, the ith coordinate squared, which is, if you know the notation of the norm, this is like y minus x theta. This is the L2 norm squared. Okay, so the L2 norm is the sum of the squares of the elements. So that's the simple way of writing this. And I try to minimize this 1 over n doesn't matter. So I could have dropped that as well. But really, you want to take the gradient. And if you've done this enough of time, you'd see that the gradient of this would be 1 over n x transpose x theta minus y. It's like a quadratic form. The gradient just comes out, but it's a matrix about the direction by x transpose. So we set it equal to 0, I get x transpose x theta minus y is equal to 0, which is equal to, I multiply, I get, move this to the other side, this is the equation. I have to solve, these are called the normal equations. And it's a linear system of equations, x transpose x I know. This Taylor thing, and then x transpose y I know. And this is solvable in general. And if x transpose x is invertible, there is a unique solution for theta. I should like back up a little bit. The uniqueness is true on x transpose x is invertible. So this is going to be convex function, but not strictly convex unless x transpose x is invertible or like full rank. So assume x transpose x is full rank / non-singular. Then I get so theta hat should satisfy this. So the theta hat solves this equation. Right, so get theta hat is x transpose x inverse x transpose y. Does that look familiar? Hopefully it looks familiar to people. So you have seen 100C, you spend like one entire quarter looking at this formula. And so that's our estimate of theta hat. So what is the estimate of the regression function? That f hat theta, or that f hat is really f hat of theta. F of basically theta hat x, which is just theta hat transpose times x. Okay, so once I have this right, theta hat, I'm going to plug in and have a linear function now. I can apply to any x I want. Okay, so that's my estimate, which I'm going to call also eta hat, because it's a regression function, and its estimate of the regression function is similar to the eta hat that we looked at. So it's an approximation of the expectation of y given x. Remember, because with the quadratic loss, the optimal thing to do, so if I do this, in not the empirical version, the population version, the optimal solution would be the regression function. Get that before getting into that analysis. So the actual like F star without any restriction on the function class is expectation. So the optimal rule compared to the optimal rule. To the optimal rule under the quadratic laws, aka the corresponding MSA risk, escape for risk, is like eta star, which is expectation of y given x. Okay. So we don't know this. We assume that it is linear, sort of, and then this is our estimate. At this point, we can't do much more. We can do a little bit more. But what we can do, any questions about this? What we can do is I'm going to assume, so analyzing linear regression, assume that eta star is also linear. So if I actually know that eta star is linear for some eta star, then what I did is a very good estimator because I'm looking within the same parametric class. So with this assumption, so there's a strong assumption, but with this assumption, then we can do a simple analysis. Okay. Next time we analyze that quantity that we analyzed for the partitioning estimator, similar thing. The conditional MSE basically. Conditional on the training axis. So we're gonna look at this. We can say this star. Or you can say eta if you want. Yeah, okay, eta star, star. So you're gonna compare this to that. Let's see if you put there's sort of nationality. Sounds good. Questions? Okay, so that's the plan for next time. We're out of time. So thank you guys. See you next time.